then one of the presenters will speak up and kind of we can answer them for everyone as well. So next, I will be spending a little bit of time talking about the statistical methods behind MSstats.TMT. So, okay, hold on, let me share screen. And here we go. So for this part, I would like to do three things, and I changed a little bit the plan based on the questions that we had yesterday. I will spend 5 minutes revisiting once again analysis of variance and lemma, because this will be helpful for us. And then we will spend a little bit of time talking about experimental design, also based in part on the questions that came up yesterday in terms of, in particular in terms of blocking. And I will tell you about how statisticians think about designing experiments with blocks involved. And then I will talk about how these ideas all come together in the methods and implementations of MSstats.TMT. So first, let us revisit a little bit the two-group t-test, just to remind you what we talked about yesterday, and if you missed the lecture yesterday as well. So essentially, if we have a simple label-free experiment where we have one feature per protein, and we want to compare healthy and disease subjects, so we will have some number of subjects with measurements on this feature from the healthy group, and some number of subjects with the measurements on this feature from the disease groups. And so our question is whether in the overall population, there is a change in the average population level abundance of the protein, whether the protein is regulated or not, for example, by the disease. And so our null hypothesis will be that at the population level, so these Greek letters represent the mean of this protein in the entire population of healthy, versus the mean of the entire population of disease is actually unchanged. And the alternative would be whether there is a difference between these population means. Now, we do not actually have the data on the full population. We only have a data on the subjects in our study. So we construct the signal-to-noise ratio, where the signal is the summary of this protein abundance in each group. And so again, we work with the log transformed feature intensities, because on the log scale, we can speak in terms of differences as opposed to ratios. So we're talking about log fold change here, right? So our signal will be the difference of protein intensities between the groups on the log scale, and our noise is describing the confidence we have or the uncertainty we have associated with each of these individual means. So it has a component of the sample variability in each group, so how much variability we have in the healthy group and how much variability we have in the disease group. And it also has a component of the sample size, so how many replicates we have in each of the groups. So the square root of this ratio of sample variance divided by sample size is called the standard error of the mean. It will go closer and closer to zero as the sample size increases, and it characterizes the uncertainty in the mean of this group. Similarly, this square root of this ratio characterizes the uncertainty in the mean of the second group. So put together, this is the uncertainty in the difference between the means. And so what we do next is we need to characterize how large is the signal-to-noise ratio. So if it's large, it means that the signal is larger than the noise. So how large is large? So if in reality there is no difference between the population means, and if we can assume that our data are normally distributed and the subjects are independent, then we can mathematically, without any data, characterize what is the range of the signal to noise, which we expect to see. Again, in the situation when there is no difference between the groups. So this is described with a probability distributions called student distribution. So this is a curve such that the area under the curve corresponds to the probability of an event. And so what we can do is to select a value, say 5%, which we allocate half of it in the left tail and half of it in the right tail. So we say, okay, these values will have 5% of probability of being observed in the situation when we have no regulation. So now what we will do, we'll calculate the actual signal to noise ratio from our data, overlay it on this graph. So if the actual observed value is in the center of the distribution, we say, yeah, well, there's as what we expect with this situation. So there is no evidence against the null hypothesis. On the other hand, if the signal to noise is too large, meaning it falls in this tail or in this tail, then we say it is too large compared to our expectations, so something is wrong. What is wrong? We assume that there is no difference between the groups. So this is evidence against no regulation in the population. And so the probability of having a false positive change when in reality there is no change between the groups is this alpha, so is 5%. And finally, the p-value, we actually overlay the observed signal to noise on this distribution and the negative value of this. And so the area to the left of the observed value plus the area to the right of the observed value together is the p-value. So if the p-value is less than alpha, then it's evidence against the null hypothesis. So fundamentally, this part with the distribution is just based on the mathematics. A very common question is, what if our data are not normally distributed? Well, the signal to noise actually characterizes the means and not the actual distributions. So when the sample size increases, this signal to noise approximates a normal distribution. And this approximation is called a central limit theorem. So this is just to review what we talked about. And yesterday we talked about the fact that there are what happens when we have multiple proteins. So we need to adjust for multiple testing. But what I would like to talk about today is how we can extend on the calculation of the signal to noise ratio. So essentially all the models that we talk about, for example, analysis of variance, or lemma, or MSstats, or MSstatsTMT, they all differ in how they characterize the signal and how they characterize the noise. And so this is really the scope of the discussion. So in particular, the first extension, and this is a classical extension, which works with more than two groups, right? So here we talked about healthy and disease. And one of the questions yesterday was, what if I have 5 groups? What do I do? So analysis of variance does exactly that. So we can have more than 5 groups. Now, a important difference, which is frequently appears in these models, is that here we talked about the signal to noise and having a sample variance, maybe I can highlight it here again, sample variance in the first group and a different sample variance in the second group. So we assume that there are different potentially variances in each group. Now, when we have multiple groups, it can be very useful to assume that even though each group has a different mean of the protein abundance, the variance associated with each group is actually the same. So now we're making a change that instead of using separate variance in each group to calculate the signal to noise ratio, we will say, let's combine the information from all the groups and have a common shared estimate of the variance across all the groups that we have. So this can be useful, especially if we have a relatively small number of replicates in the study. So if this assumption is plausible, if we're still interested in comparing two groups, we can still compare this mean to this mean. However, we will use all the data to learn the variability in the underlying populations. So even though we compare these two groups, we will use all the data to better learn the estimates of variation, because this now combined estimates of noise will be based on more than just two groups. It will be based on 5 groups. Of course, the price for this is that the assumption that all the groups have the same variance. And so this is something that needs to be checked, or we just need to kind of see if we can reasonably assume that. It is possible there are versions of analysis of variance which do not assume constant variance, but for the purposes of our discussion, this is really what is happening. And in fact, this is what MSstats and MSstatsTMT assume in their models, because the alternative is, especially with a small sample size, we need to have a separate variance learned for each of the groups, and it can lead to overfitting, especially when we talk about applying the same model over and over to many proteins. So this is, so borrowing this variance across multiple groups, even if we're interested in pairwise comparisons between the groups, this is one extension of what we discussed yesterday. So now we have this common estimate of variation and the combined sample sizes. So now the second extension, and this was another question asked, is focusing on lemma. And so lemma continues on this theme of learning the variability better, but goes one step further. So even though we combine the estimates of variability across all the groups, it may often be insufficient when the sample size is really small. And by small, I mean 2 or 3 replicates per group. More than that, it can be reasonable, but 2 or 3 replicates per group, this estimate of sample variation from the data can be very unstable, meaning if we repeat the experiment once again and collect new data, our estimate of variation can be quite different from the estimate of the last experiment. And this can be a problem because, of course, in the signal to noise ratio, noise plays a very important role. And it results in our conclusions being very unstable. So lemma attempts to bring the stability to this estimation in experiments with small sample size. But it does it by borrowing information further. So analysis of variance assumes constant variance across the groups. So lemma will assume not only a same variance between the groups, but also same variance across all the proteins. So what I just said is actually not quite true. So it doesn't quite assume the constant variance between all the proteins, but we can think of this as an extreme, right? In the extreme case, if we assume that not only all the groups, but also all the proteins have the same variance, we would have a lot of data to estimate this, right? But of course, biologically, it is very unlikely that every protein has the same variance within the group and between the groups. So this is extremely restrictive. So lemma takes a middle ground and says, okay, let us have the estimate of noise in the signal to noise ratio being a weighted average between the protein specific estimate of the variation and the estimate of variation, which assumes that all the proteins come from the same distribution. So specifically what is happening is that we will proceed by estimating variance separately for each protein. And then we can essentially draw a histogram which looks at the inverse of these estimates of variation across all of the proteins. And so to this histogram, we can fit a curve which corresponds to the chi-square distribution, which is scaled by this quantity s square 0, and it has another parameter, which is the degree of freedom. So you can think of this s square 0 as the consensus variance or kind of shared variance by all the proteins, and the d0 is the shared amount of data that went into estimating this quantity. And so now what lemma would do, it would use the estimate of noise here, where the estimate of variation is a weighted average between a shared variance between all the proteins and the protein specific variance. And the weight associated with that is again this degree of freedom. So both S0 and D0 are learned for the particular data set. So actually the method is fairly rigorous. So there's a lot of rigor that went into that, but fundamentally for the applications, this is really what is happening. So it affects this noise, the definition of noise in the signal to noise ratio. So in other words, lemma says, now my noise, not only borrowing variation across all the groups, but it is also borrowing variation across all the proteins. And so one of the original publications kind of showed the impact of that. So if you have an experiment with a small number of replicates in the volcano plot, there is a limited agreement between the fold change and the statistical significance or practical significance and statistical significance. After moderation, the volcano plots become more aligned, meaning that the noise now is a lot more constant between proteins, so a lot more similar for all the proteins, meaning fold change plays a more important role in statistical significance. And so now the fold change is much more consistent with the statistical significance. So again, this comes at the cost of the assumption that we can share some of the information about variation between the proteins. Are we talking about absolute or relative variance here? I assume relative variance. I'm not sure what absolute variance is. So um, the data we talk about here are all coming from relative quantification, right? So we do not have absolute quantification as in, assays which give us the exact amounts or concentrations of proteins, right? So our data are signals from the spectra. So if you want to know what variance is, well, this is the actual formula of the variance as it is calculated for one group, right? So this is literally taking the intensities of the peak in each run and looking at the deviation from the mean intensity in the run squared, right? And then standardized. And we do the same for the second group. And so now if we look at the combined estimate of variation, it will look like that. So this is all based on relative peak intensities, and it is all just looking at the deviations of individual intensities from the sample mean. What do we mean by moderation? Moderation is exactly this process where the variance, so in the noise, so in the denominator, becomes the weighted combination of the variance specific to the protein and the shared variance between all the proteins. So essentially, you can think of the protein-specific variance pooled towards the constant variance across the proteins, right? And so this is what is called moderation. You can think in the extreme case where this D0 is much, much larger than D. So essentially, the protein-specific variance plays no role, and it means assuming that every protein has the same variance. When the sample size in our studies increases, typically D0 tends to become smaller. So this term actually becomes negligible. And so then it is as if we actually work with the protein specific variance. So so moderation is pulling the variance away from what we learned from the data towards a single shared variance across all the proteins.
Okay, one more question. Yes.
Could one relate estimate the variance to abundance level? Lower abundance having a larger variance in general. Correct. So um, this is why MSstats would not really rely on this type of moderation very much. So typically we would use separate variance for each protein. Now, if in most proteins that we have seen, the fold changes are really small. And in fact, the proteins we're interested in, the fold changes will be uh, subtle. So therefore, if a protein is low abundant, the variance across the groups will be protein specific, but we can, I think, reasonably assume that it is the same between the groups. But the variance for low abundant protein will be very different from the variance for high abundant protein. This is how MSstats would work, and this is how analysis of variance will work. So lemma will, that's the price you pay when you use lemma. Now, it can happen that you have, I don't know, a knockout or some really strong stress which changes the abundance of the protein between the groups. So that in one group it's very low abundant, in the other group it is high abundant. Those cases are comparatively rare as compared to other proteins. So then analysis of variance or MSstats will use some kind of average variance between the groups. But in this case, typically the fold change is so large that it doesn't really matter. The signal to noise will be large anyways. So I think it is more important to estimate the variance correctly when the fold change is small. And therefore, it is more important to have separate variance for each protein. This is my opinion. And finally, let me again reiterate that when the sample size is large, this weight of the protein-specific variance dominates. So moderation really doesn't play a whole lot of role when the sample size goes beyond 4 or 5 replicates. So in my experience, many people use lemma in large part because of the nice implementation that is available, which is a very good reason. But as we mentioned yesterday, it is limited in terms of what kind of signal it can characterize, what kind of combinations of sources of variation. So in particular, it cannot easily express time course or paired designs. Okay, so now let me move on with that. So I hope that this was useful. So now we will talk about how we actually work with experimental designs in terms of characterizing different sources of variability. Let's see. So let me just take a step back and tell you about what happens in my mind when we design a new experiment and we talk about statistical models and how we detect regulated proteins. So this is what we're interested in. So there is a population, let's say, of healthy individuals and another population which has the same characteristics as far as age, gender, risk factors, except for the fact that this population has the disease. For all practical purposes, these populations are infinite, meaning we cannot measure every single the abundance of proteins in every single subject. So for this reason, we select subjects, a subset of these individuals in the study, because we select them randomly. This is the first source of variation. This is biological variation. And if we are to repeat the experiment, we will include some other subjects in the study, and therefore we will not have exactly the same protein abundances in our samples. But this is not the full story, because now we actually need to quantify the abundances of proteins using a measurement system such as mass spectrometer, which itself has some noise and variation associated with that. And so, because again, if we take the same sample and remeasure it multiple times, we will not have exactly the same values. So this is the technical variation we have to deal with. And so what we're interested in is comparing the populations, but what we actually observe is the intensities of spectral peaks. And so the process of statistical inference is to take what we observe and to make conclusions about what we're interested in, which is not observed. So in general, inference means making statements about what is not observed from what we actually observe. And now the challenges associated with inference are at least twofold: the bias and inefficiency. Bias means that what we see in our data, or what we conclude from our data, is systematically different from the truth. And the bias is the worst type of challenge, because bias is reproducible. Because if we design an experiment incorrectly and we again make the same mistake, then we say, oh, look, we reproduced our results, but in fact we were reproducibly wrong. So this is not what we want. And inefficiency is another challenge, where our data just have so much noise and variation associated with them that we cannot say anything meaningful about the underlying population. And so the objective of experimental design is minimize the bias and inefficiency. So make sure we're not systematically wrong, but also make sure that we can get as informative data as possible given limited resources. So this is really what this is about. And just to come back to the notation, we use Greek letters for the unknowns. We use Latin letters for what we observe. Again, on the log scale, we have some summary of the data, in this case, the signal. Then we need to characterize the noise, and we will use the signal to noise ratio to make some statements about the uh, the quantities in the populations. And so the bias means that what we see is systematically different from what we're interested in. And inefficiency means that we have so much variance, so much noise associated with the measurements that we cannot say anything useful. Okay, and so these two challenges can be prevented by three principles of experimental design. The first principle, I hope I do not need to convince you very much that we need to have replicates, right? The first principle is replication. So if I have only one measurement from healthy and disease, so is it a systematic change or is it an artifact? The answer is nobody knows, because here is what happens for this particular change. If our replicates, let's say biological replicates, are very tightly grouped around the population mean, so this is unlikely to be an artifact. This is what happens when our replicates are spread quite a bit around the mean. So this difference in the mean can be very well an artifact of random variation. So the replicates allow us to characterize how much variation we have in the system, and it also allows us to say how much confidence we have in the individual means. So two things to say is, one is just comparing these two figures, I hope you can see that fold change alone makes no sense whatsoever, right? Because the same fold change may or may not be an artifact of random variation, or may or may not be systematic. So we clearly need the signal to noise ratio and not just the signal to claim what is systematic. And the other thing is that the number of replicates clearly has implications, because even if in this case, when we have large variability in each group, if we have many, many replicates, then we will be very, very confident in this mean and very, very confident in this mean. And we can still say with some confidence that this change is not an artifact. But in this case, it will require a much larger sample size than in this case. And because we have two types of random variation, biological and technical variation, we also have two types of replicates, biological replicates and technical replicates. The question about the random sample of individuals, is it a complete randomization or a simple randomization? I don't know what's the difference between complete randomization and simple randomization, but hold that thought, because hopefully the next few slides will clarify some of that. Okay, so for the moment, we're saying that we just randomly select subjects from the population and randomly allocate them to all the steps of data processing. So maybe just before we get to this, so let me just, as I said earlier, we have two types of replicates, biological and technical replicates. So how do we mathematically characterize the effect of replicates on our conclusions? So just like earlier, I talked about analysis of variance, how it extends to sample t-test to more complex situations, such as multiple groups. So analysis of variance can be extended further to also characterize different layers of replication. So here was an old study that we had, which was looking at individuals with diabetes. So there was a disease group, healthy versus disease. There were multiple replicates, so there were two replicates per group. So the overall intensity is affected not only by the mean of the group, but also by the which individual the observation came from. But then each sample was prepared multiple times. There was an enrichment step. And so each sample actually was enriched separately twice. So also the observed intensity of the features was also affected by the sample preparation. And of course, there is a measurement error. So the statistical models, such as analysis of variance, can be extended further with this type of approach, which takes the overall variation in observed variation in feature intensities and decomposes into these known sources. Okay, we have multiple groups, we have multiple subjects, we have multiple individuals, multiple sample preparation, and multiple mass spectrometry runs. And so just like in the t-test, I could write mathematically what the noise would be corresponding to the signal. When we have these complex layers of variation, I can also write mathematically what the noise will be associated with the signal in a situation when I can decompose sources of variation. So long story short, you see that there is number of replicates associated with each of the terms of these variances. In particular, if I increase the number of technical replicate runs, I will reduce this component of the variance. If I increase the number of times I do sample prep for each sample, I will decrease this component of the variance. But if I increase the number of biological replicates, this will reduce the overall noise associated with the signal. So in other words, biological replicates are the most principled way to reduce the noise associated with the signal. So if you have a fixed number of runs, you are much better off allocating these runs to different biological subjects rather than quantifying the same subject really, really well, but you still have only one subject. So this is how statisticians think about this type of experimental designs. And also yesterday we talked about data being independent. So clearly multiple sample preps coming from one individual will be more similar to each other than sample preps coming from different individuals. So this type of extensions to the models can account for the fact that our data are not independent. So there is a way to accommodate for lack of independence from known sources. So the problem is when the independence is violated by sources we're not aware of. Okay, so this was to say that replication, sorry, replication is an important principle, and that the biological replicates are the most important because they are the most principled way to reduce the noise associated with our signal. So now going back to the question about randomization, so hopefully we can kind of understand that randomization is also important, because if we collect all our data from the healthy subjects on the first 2 days of the experiment and all the data from the disease subjects on the second day, 2 days, then the difference we observe is due to both the disease but also to the day of data collection. And so randomly allocating subjects to all the days will inflate our variability, will inflate our uncertainty associated with the overall process, but at least it will not have the bias. And so because again, we have two sources of randomness, we have two types of randomization. We need to randomly select subjects from the population, and we need to randomly allocate all the samples to all the processing steps. And so now we're coming to the most relevant topic for us for this presentation is the blocking. So blocking is a strategy to account for known sources of variation and reduce the noise associated with the signal. So as we have seen just before, if I completely randomly assign all the subjects to different days of data collection, it inflates the variation associated with each group. Because now the variation in the group is due to the biological variation, which is just normal person-to-person variation in this population, but it was also due to the day effect, right? In some days we inflate, like the measurements are high, and in some days measurements are lower. If we know, for example, that we have a day-to-day variation, but we cannot do anything about this, but we know it exists, then it is more effective to allocate systematically the samples from both healthy and disease on day 1, allocate samples from healthy and disease on day 2, same for day 3 and day 4. So blocking is, in fact, a restriction on randomization. Maybe this is what the other question meant. So blocking is a restriction on randomization where we impose on day 1 to have the same number of healthy and disease. So we'll still select healthy and disease randomly from our study. We will still randomly assign the order in which they are acquired, but they're all acquired on day 1. So this has two advantages. One is that this way we know that we have every healthy subject was acquired among all the days, and every disease subject was acquired across all the days, so we have no bias. But we can also at the same time improve the efficiency of the experiment. So now instead of comparing the mean of this group to the mean of this group, we can look at the systematic differences between healthy and disease on day 1 separately, on day 2 separately, on day 3 separately, and day 4 separately. And so even though within each group we have quite a bit of variation, we see that within each day, our differences are pointing in the same direction. So here the disease is upregulated systematically compared to healthy. So by considering differences within days, we actually gain sensitivity, even though we do have this day-to-day variation that we cannot eliminate experimentally. So this is what blocking is doing. So blocking has two components. One is allocating the resources by imposing a restriction on randomization and making sure that we have representatives of healthy and disease, for example, within the same day or within the same sample plate or whatever batches of materials that we have. But it also takes a second component, which is the analysis. Because if we do not analyze this experiment as if it was a blocked experiment, we would not gain efficiency. So we will reduce bias just by the design, but also by changing our analysis strategy, we improve the efficiency. So blocking is really the most advanced technique, and this is where the expertise of a statistician is the most important, I would say. However, just the design itself helps you eliminate the bias, and it is already quite a lot. And so now again, the same story, since we have two levels of variation, biological and technological variation, we have two levels of blocking. So one blocking is due to the technology, such as day-to-day, as I described here. But the other is blocking with respect to biological characteristics, such as risk factors. And as I mentioned yesterday, age and gender will be very obvious in clinical studies. This will be the very obvious blocking factors. But they can be others, such as weight, smoking, or maybe some other diseases or whatever else is relevant in the particular context. So especially if we have a small number of replicates, if we randomly select subjects into the study, it can just so happen that all the healthy are, I don't know, older and heavier, and all the disease are younger and lighter and females. So blocking will make sure that we have the same number of younger females, the same number of older females, the same number of younger males included in the study. And so blocking just at the experimental design stage will eliminate the bias. Accounting for this in the analysis also helps reduce inefficiency. And now I just want to clarify that even though my cartoon here looks at the pairs and looks at the differences of pairs in each day, of course, we can go with blocks larger than 2, and we can have multiple blocks, and models such as analysis of variance can be extended in similar ways to account for these fairly complex blocking structures. But again, we have to be careful and avoid overfitting. And so this is how we actually go about that. So same idea, just like analysis of variance was extended to multiple groups, we can describe the overall variation in the observed feature intensities in terms of the contributions of the disease group. This is what we're interested in. This is the random variation due to the, let's say, day that we have. So this is the day-to-day variation. This is the random variation person to person. And this is the random variation, for example, between mass spectrometry runs. Same idea. We can mathematically derive what the noise would be associated with our signal. In this case, it is this formula. And so now we see that this variance of the block, so in this case, day-to-day variance, appears as a term. So if we completely randomize without blocking, this is what the variance would be. But if we randomize, apply the blocking, and analyze the data as if the design has blocks, we essentially eliminate this component of variation from our noise. So we gain efficiency in our signal to noise. Now, how much efficiency we gain? Well, it depends on how much block variance we have. So for example, if we do not have day-to-day variation, but we go into all the trouble of blocking and so on, we actually don't gain much, but we can make mistakes, and we also can overfit our data. So at the stage of experimental design, it is useful to have this pilot study to understand how much variance we actually have due to these potential artifacts, and decide whether it is worthwhile going into the trouble of blocking or not. Because again, the price of this is a more complicated experiment and potential overfitting. So blocking is useful when it is necessary, but it can also be, we shouldn't overdo it, right? And so there's a value in simpler experiments when this variance of the block is actually relatively small compared to biological and technological variance. And so we can make curves like that to say, okay, this is what happens when the variance due to the block is large, but this is what happens when the variance due to the block is actually relatively small. Are we able to show a real world example of blocking? A lot, because the reason why I'm talking about that is that the most kind of specific example of blocking is multiplexing. And so when we use label-based experiments, this is probably the most obvious example of blocking. Now, if you want to know more about blocking in general and look at the real-world examples, I have this reference here. A lot of these figures come from this paper, and we do provide some examples. So take a look at this publication. It spends a lot of time talking about all of these experimental design strategies. But for the purpose of today, our most important example of blocking is multiplexing, because now our mass spectrometry run is a block where we acquire simultaneously data from multiple subjects and hopefully from multiple conditions. And so whatever run-to-run variation we have will be eliminated by blocking within mass spectrometry, within the mass spectrometry run. So this is exactly kind of the segue of the topic of our discussion today. So if we have a label-free experiment, this intensity of the healthy subject versus disease subject, they are affected by whatever happened in this run versus this run, especially if these two runs have been acquired fairly far away from each other in time. And so, well, this is an older review. This is iTrack. Obviously, now we're doing TMT, but same idea. So if we can label peptides chemically, they are now pooled together in the same run. And whatever artifacts or interferences happen to this particular peptide in the mass spectrometry run, it will be shared by all of the samples which are pooled together. So this is, of course, a very effective technique. So not only in terms of increasing the throughput of the experiment, but also from the statistical perspective in terms of accounting for run-to-run variation. Of course, it comes at a price of the complexities associated with the labeling and literally price and dollar amounts, because those agents, labeling agents, are have a price associated with them. And of course, when the experiment is more complex like that, there can be artifacts associated with the labeling efficiency or some other issues. So there are many experimental issues that need to be controlled. But this said, just from the pure statistical perspective, if the experiment can be done effectively, this allows us to reduce the unwanted variation, which comes just from the differences between mass spectrometry runs. So this is potentially a very good thing if it is done well. Before we go to the MSstats TMT, so let me first, also from the same publication, share with you how statisticians think in general about this type of experiments. So in this example, if we have, let's say we have a multiplexing experiment with 5 channels, and if we have 5 disease groups. So it is very clear that we will be much better off having one subject per group within each block, right? As opposed to measuring 5 times group 1 in the first run and then 5 times group 2 in the second run, right? So I hope it is very clear that it is best to have one representative from each disease group within the block. And so then if we have more than one replicate, which we should, right, then we have a second block, which will have another set of representatives from each disease group in the next run, and so on and so on. And so we have essentially as many blocks or as many runs as replicates, right? And each block will have representatives of each disease group. Now, the problem is, of course, that it is very difficult to have an experiment where the number of groups is identical to the number of channels and so on. So we usually want to do things in a more flexible way. So this is a situation, what happens when we have more groups than labels or channels. And this can happen, for example, if you have a time course experiment and you have, let's say, 11-plex experiment and you have 15 time points, which are very important. So you cannot fit all the conditions and all the time points in a single block. And there are many ways to allocate conditions to blocks. It turns out that just the same way as we have been extending these models to account for sources of variation and calculate the noise associated with the signal, we can do the same thing for these different designs. And it turns out that a systematic restriction on randomization, which now says, okay, let's make sure that in different blocks, different disease group is missing, so that different subsets of groups, but always in a balanced way, are present in various blocks, it will reduce the noise best. So it will maximize the efficiency. And this is an extreme case where we have 5 groups and only 2 labels, let's say if you did SILAC. So there's also a way to allocate samples to these groups in a way that minimizes to noise associated with the signal. And so this is the type of calculation statisticians would do. We can even draw these curves for different type of variants. And so there are ways to effectively allocate samples to channels when the number of conditions doesn't match or is not like a simple rounding of the number of samples. Okay, so let me see if there any way. So let me leave these questions for later. Let me first make sure that we talk about MSstats and then we will try to address some of these questions towards the end. Okay, so MSstats is designed for this type of multiplexed experiments. And so just like yesterday, we talked about this data structure that we have in label-free experiments. We now have a similar but modified structure in multiplex experiments. So the important part is that, so again, the rows are as before our features. And in label-free, it can be fragments, transitions, or peptide ions, right? So here, our features will be MSMS spectra corresponding to individual peptide ions, right? So each feature is a peptide ion. And so there are multiple distinctions now between these data structures. In label-free experiments, the runs are grouped by subject, and subjects are grouped by condition. But now the situation is flipped because we have biological replicates within conditions, just as before. And let's say for simplicity, we have, I don't know, 2 groups or 3 groups, and we can fit multiple replicates of each group within the same plex. But now they are all grouped by the same mass spectrometry run, which can potentially be grouped by the same mixture if these mass spectrometry runs are technical replicates of the same mixture. So they will all have the same biological replicates between the runs if they are from the same mixture. And then, of course, we have another mixture which have new biological subjects. So just in the terminology is that the mixture contains different biological material. Mass spectrometry run can be technical replicate run of the same biological material. And this biological material is a combination of biological replicates which come from different conditions. So now the grouping is different. And what is important is that the top level of the grouping now is actually a random factor because the mixtures contain some randomness and mass spectrometry runs contain some randomness. Whereas before the condition was actually fixed by our experimental design. So this means that we need to change the statistical models that we use to decompose the sources of variation and characterize the signal and the noise for each protein. And this is why MSstatsTMT is a different package from MSstats because the models are quite different and a lot of things are fairly different. And there's another issue here. So if you look at the values inside the cells, so X here means that there is some value present and NA means that some value is observed. Remember in label-free experiments, we were saying that it's often observed because the ion is below the limit of quantification or below the limit of detection. Well, in MSMS, it can be fairly different because maybe the peptide ion was just not selected for fragmentation, or maybe it was not confidently identified by a database search engine. So we will have a lot of patterns that the same peptide ion will be present in one mixture or in one run, but then absent in other runs. So we have the nature of missing values, which occurs here, is very different from the nature of missing values in the label-free experiment. So we have to deal with this as well. So how do we proceed? Well, we kind of mirror the workflow for the label-free experiment with important modifications. So in terms of the experimental design, well, as we have seen, there are many options of allocating samples of mixtures. And it is very important to think through to make sure that the way we allocate samples and conditions to the mixtures is efficient. So just by design, it minimizes the uncertainty associated with our signals. And of course, we can have multiple mixtures, potentially multiple technical replicates, multiple biological replicates, and so on. As you will see, we very much recommend allocating at least one channel for a reference mixture. So this is some type of mixture which is not expected to be changed in abundance between mass spectrometry runs. So it is added in a constant concentration, and it serves 2 purposes. One is that we can normalize the signals, especially due to issues like here, where some ions are observed only in some runs. But it also helps, for example, if it just so happens that the protein is low abundant in all the biological samples, at least the reference channel will be abundant enough to help this ion be selected for fragmentation in the mass spectrometry run. And of course, many experiments actually have multiple fractions, which is fine too. So MSstats handles multiple fractions uh, in a very kind of natural way. Okay, so once the experimental design is thought through and the data have been collected, so the data processing is, so the input that MSstatsTMT takes is in form of a list of identified PSM with quantified reporter ions. So currently, and Ting will correct me if there are any modifications, but currently we take as input, so we have converters from Proteome Discover, and Proteome Discover actually has a scripting node from Thermo, so you can actually do this even through the graphical user interface, MaxQuant, OpenMS, and SpectroMine. So Ting will maybe clarify this further. And the converters do a lot of other things other than formatting. For example, currently the MSstats workflows are based on uniquely identified peptides, so it will eliminate peptides shared between multiple proteins. It can filter out PSMs where many reporter ions are missing. For peptide ions with multiple PSMs, keep the best PSM in terms of the intensity, missing values, and interference score. And so combining the fractions, it's also happening at the converter step. So Ting will also talk about this in more details. So after that, it is time for statistical analysis, and this is really where the core of MSstats TMT happens. By the way, in terms of this processing, if you are not happy with some of the steps, you can very well implement your own processing steps because there are some options, but you can also write your own scripts so that you can jump straight into the analysis steps as opposed to using the MSstats converters. So because we have more complexity here, we actually have 4 steps where we have first normalization at the spectral level, second the summarization at the protein level, then another round of normalization at the protein level, and statistical modeling and inference. So let me walk you through this. So the first step is kind of similar to what we would do in label-free experiments. So MSstats will make plot like that, where now we have box plots of all the reporter ion intensities across all the peptides and all the proteins in this run, which are now separated by channels. And so you see here for this particular data set, there was slight variation the between the channels, possibly due to some differences in labeling efficiency, although this is known to be fairly minor, or some other artifacts. So similarly to label-free experiments, we would assume that, especially in this type of experiments, the change in abundance between those channels occurs for a relatively small number of proteins, so we will equalize the medians of these intensities. Again, all proteins and all PSMs combined. So this is just to ensure that our signals are stable at the global level, so without considering differences between the proteins. The second step will consider all the PSMs. So now this is per protein. So now these are all the features which belong to this protein in run 1, in run 2, and in run 3. And so you see that between the runs, there can be quite big differences in average intensity of the features because, well, this can be different features in the first place, right? This can be different ions in different runs. So this is to say that things are not comparable between the runs yet, but things are comparable within the run. And so what MSstats will do, it will take each run separately and it will summarize the protein abundance, just like in a label-free case, by using all the features and all the intensities that we have. And we treat missing values at this stage within each run the same way as MSstats. So now that we have summaries, again, this is just one protein, and the lines here will be the summary obtained across all PSMs at the level of this protein. And now we need to make sure that this is comparable between the runs. And this is where we use the reference channel or channels, if we have multiple channels, to make sure that we can now account for differences between the runs, which are due to whatever happened with mass spectrometry intensities in different runs, but also to account for the fact that in different runs, we actually have different peptide ions. And so some of these differences are just due to the fact that different ions represent this protein in different runs. And so the reference intensities are shifted so that they become constant between the runs. And then the same shift is applied to all the endogenous signals within that particular run. So we do equalize the reference channels here, and this is protein specific because different proteins have their own PSMs, which are not comparable between the runs. A frequently asked question is about what happens if we don't have reference channels. And well, it is worse, to be honest, because then the only thing that we can do is to assume that the average signal across all the channels in run one should be comparable to the average signal across all the channels in run two, and so on. But this is a really strong assumption because we have a relatively small number of channels. There can be really actual differences in biology, which we will eliminate by doing that. So we have worked with different flavors of that, and we found that without the reference channel, we essentially throw away the baby with the bathwater to some extent. So it is more effective to use reference channels and adjust the intensities of endogenous signals with respect to that amount. So this is what we do here, and then the next step. This is the core of MSstats in terms of statistical models and inference. So we need to represent the experimental design, which is non-trivial because we can have different configurations of subjects and conditions in different plexes, represent peak intensities, and of course characterize the noise associated with the signal. Similarly to MSstats, we could potentially have a full model associated with this data structure. We do not do that. We work with the summaries, so we take as input for statistical modeling these summaries at the protein level, which have been normalized. And this is a much simpler model, which is much less likely to overfit, is more numerically stable, more scalable to large number of proteins. So we work with this type of summaries. We again extend analysis of variance or similar models to characterize the contributions of various mixtures, potentially various technical replicates, conditions, and subjects, and then we derive those signal-to-noise ratios, which allow us to make pairwise comparisons between conditions. And so since oftentimes these experiments still have a small sample size, Ting actually added this empirical Bayes variation, variance moderation from lemma. So where you have an option to assume that your noise associated with the signal is a weighted combination of the protein-specific noise and the shared noise across all the proteins. Again, to be used with caution because it's a very strong assumption, and typically it doesn't really make any difference beyond 3 replicates per condition. And of course, as always in MSstats, we try to use this as a pilot study for future investigations, so we can produce this type of sample size calculations. And we also work with massive and massive quant for submitting the results. And we will talk about massive quant actually tomorrow. So I hope that you will stay in for that. So now let me finish here. So before I stop, let me make sure to thank Ting, who was the main driving force behind the entire MSstatsTMT development and very extensive benchmarking. And of course, Mina and Mateusz, who contributed an enormous amount of work to also evaluation and new developments. And thank the entire group who contributed to MSstats, as well as our collaborators across multiple institutions, in particular Genentech, who has been very supportive of the TMT work, and we have done some of the initial developments in collaboration with those groups. Okay, thank you so much. So now let's see if there are any questions that I can answer. So there is a couple. Can you comment on the effect of carryover on blocking design to include blank runs, etc.? I think this is very specific to your workflow and the nature of the samples. Carryover will be a problem for every experiment, blocking or no blocking, right? I would say that without knowing more, what statisticians would always do is to have a pilot study. And it is always a good idea to have a small scale pilot study just to understand how much carryover there is. And so you can have two versions with and without the blanks in between and try to understand what the implications are. And usually for this type of pilot studies, we like to work with some samples where we have a sense of the ground truth, such as controlled mixtures or spiking experiments or some biological samples with known biology, so that you can uh, characterize the extent of carryover. So clearly blank samples help, but I also understand that having them between every run is not practical. So I won't be able to say more or like other than just consider empirically the effect of that and try to adjust your workflow based on your own data. Um, could you please repeat in which cases we need a reference channel? I would say always. So essentially, the purpose of the reference channel is okay. So we do not need a reference channel if you only have one mass spectrometry run. If you have a experiment with two conditions and you have 5 replicates per condition, and you can fit everything into one run and just do one run and you are done, then you do not need a reference channel. And this is a possibility. Of course, it also means that you are limited to a very small number of replicates, and also if something goes wrong with your run, that's the end of it, right? So as soon as you have more than one run, then we do recommend reference channels because they help us make things comparable between the runs. And the difference between the runs is fairly substantial because we can have different ions representing the protein in different runs. These ions have different ionization efficiency, different interferences, different, everything. And so we cannot compare the intensities of reporter ion channels in one run to the other run directly just because they come from different peptides. And so the reference channel helps us shift the intensities between the runs, which essentially account for that. And this will allow us to integrate measurements from the reporter ion channels in run 1 together with reporter ion channels in run 2 and so on. And then we can put them all together in this type of statistical model. So now they are comparable and we can use them to characterize the sources of variation across the entire experiment. So to summarize, if you have more than one run, reference channel is very helpful. We experimented with multiple reference channels and they help, of course, but we feel like the loss of biological replicates is probably a bigger problem. So one reference channel is already quite reasonable. Um, I do not see why the reference channel normalizing went to log intensity after normalizing that specific protein. So we work on the log scale from the very beginning. So when we have the input, so this type of input from different tools, I didn't say it here, but one of the first things we do in the converter is to apply a log transform. Again, log 2, log 10, you can choose, but on the log scale. So everything is compared in terms of means and medians, right, as opposed to ratios. So in particular, already here, when we do the global normalization, just to make sure that some systematic differences between channels or runs, which are not specific to individual proteins, are accounted for, it is already happening on the log scale. And so we keep log scale throughout. So after that, we do the summarization on the log scale, and this includes the reference channel. So let's say in this data set, the first and the last channels are reference channels. So they're summarized just as any other channel. across all the features which are present here. And so now these are the summaries. So these are the summaries of the endogenous intensities, but we have a similar and obtained in the same way summary for the reference channels. And so now we just shift. So you see that this red line is the kind of the mean or the median, some central value for the reference channels. And so what we will do, we will shift all the references so that all line up on the same line. And we apply the same shift. So for example, this value was on the red line. Now it became shifted up because this reference channel was shifted up a little bit. So that's all there is. So we do not kind of change log or no log. Everything stays on the log throughout the analysis. And again, because on the log scale, we can apply transformations in terms of pluses and minuses as opposed to ratios because it has more numeric stability and has better statistical properties. Okay. So let's see. Could the reference channel for MSstatsTMT with something like Basel be used? I see Ting is answering. Okay, so let me just let Ting answer that. What about if I always want to make a comparison within a mix in an equivalent manner to pair t-test? I guess the question is, what if I want to make a separate comparison here and a separate comparison here? Well, eventually you have to put it together, right? So if your various mixes have the same conditions, so just like in regular blocking, let's just revisit the regular blocking. So in the regular blocking, what we said is in the same day, I have one healthy, one disease. I'm looking at differences between healthy and disease. On the second day, I also have healthy and disease, and I have one difference. On day 3, I have one difference. On day 4, I have one difference. So yes, you did a paired t-test, but I mean, within each day, but you now ended up with 4 differences, right? So what paired t-test would do is now to test the null hypothesis that the population mean of these differences is 0. And so you would need to combine these differences in a single model to test this hypothesis. So this is exactly what is happening with these extended linear models that MSstatsTMT implements and others. They combine these within mix comparisons in a single signal to noise ratio, right? With the caveat that you may have more than 2 measurements in one block, right? So in particular, if you go back now to MSstatsTMT, so if we have one mixture, right, and we have multiple conditions, you have some replicates. So you have some signal and some noise, right? You will have the same thing in this mix, some in this mix, and some in this mix. But eventually you need to put it all together to have a single signal to noise ratio. And so the models which I described here do exactly that. So it is a general model which says it doesn't matter how conditions you have on the same mix, how many replicates you have on the same mix, how many runs you have. So these models take all the data together because they're already normalized and they're already comparable, and it will decompose the contributions of mixtures, replicates, and etc. And so they do exactly what you say. So they're already accounting for blocking, but they're also putting all these differences together in a single signal to noise ratio and in a single p-value. If one sample is limiting, okay, well, yeah, so I see that Ting is answering that as well. So we can probably leave it at that. So we are somewhat over time. So let us take a 7-minute break and let us come back at 12:45 for the hands-on. And I'm sure that Ting will be able to answer some of your questions as well. But I will also be answering questions in the Q&A. So if you have questions to me, please do not hesitate to continue asking these questions. So let us take a 7-minute break and we'll be back at 12:45 Eastern